in this video, we are going to start the basics of chemical bonding, and then we will move forward to study the models of chemical bonding, starting from the Levy structures. So there are certain fundamental interactions in the bond formation. So whenever a chemical bond is formed, certain interactions takes place between two atoms. We are going to take the examples of hydrogen atoms, two hydrogen atoms. They are represented here. You can see the circle, and the H plus, it represents the nucleus, and this circle represents actually the orbital of the hydrogen atom. And we label this hydrogen atom as A. Now this is another circle which represents another hydrogen atom B, with the positive charge represents the nucleus, and the electron which is circling this positively charged nucleus. So whenever we have two hydrogen atoms separate at a certain distance, then this situation is called as the separated atom limit. When the two hydrogen atoms have no interaction between them, but they have only the interaction of the nucleus with electron, and similarly in the hydrogen atom B, the interaction which is present is between the nucleus and the electron, and we have no interaction between two hydrogen atoms. So in the separated atom limit, or in the separated atom state, the only interaction or force of attraction which is present is between the nucleus of the one hydrogen atom and its own electron, and similarly the nucleus of the second hydrogen atom and the electron. Now in the formation of the bond, the two hydrogen atoms, they will start to come closer towards each other, and as a result of this movement, some more interactions will take place between these two hydrogen atoms. So let us see that what are these interactions that take place when the two hydrogen atoms they come closer to each other to form a bond. So in the bond formation, what happens that the atom A, which is this one, here you can see that this electron of the atom A, it will start to experience the force of attraction from the nucleus of the hydrogen atom B, as represented by this blue line, and similarly this second electron of the hydrogen atom B will also be attracted to the nucleus or the positively charged center of the hydrogen atom A. So what will happen as the two hydrogen atoms they come closer to each other, the new force of attraction arises, which I have represented by this blue line, and I have written this attraction in the blue as well. And similarly what happens is that there is a repulsive force between the two hydrogen nuclei because they are positively charged. So when these two atoms they come closer together, there is a repulsion between these two positively charged nuclei that I have represented with this yellow line. And also similarly, because these two electrons are negatively charged, so there will be a repulsion between these two electrons as well. So you can see that two more kinds of interactions they arise as the two hydrogen atoms A and B they come closer to each other. So actually there is an energy of interaction which is associated with these two hydrogen atoms when a chemical bond is started to form, and this energy of interaction is basically the sum of all these interactions, that is the nuclear repulsion plus the electron nuclear attraction and the electron repulsion. So it depends on these three forces that whether a chemical bond will be formed or not. So actually this attraction between the electron and the nucleus of the other atom should be higher in order to form a bond between the two hydrogen atoms. So these are kind of interactions that arise when the two atoms of any element they come closer towards each other. And these are the fundamental interactions. It means that they are common to all atoms, not only for the hydrogen atoms but also all other atoms of the elements. Now keeping in mind these three kinds of interaction, we can draw an interaction energy curve between the two hydrogen atoms. And this is actually the interaction energy curve. It looks like this, and it comes from some calculations that we are not going to discuss in this lecture. All which we want to discuss here is that there is the distance between the two atoms, which is plotted on the x-axis, and on the y-axis we have the energy of interaction. So here you can see here this zero line, and here below zero line we have the dotted line. So first we are going to start to study from here. You have two hydrogen atoms. This is the separated atom limit, where we have two hydrogen atoms at a particular distance and there is no interaction between them. And as these two hydrogens they come closer to each other, what happens that the interaction energy decrease. And as you can see from the curve, then this line is going here because you have the distance on the x-axis, so you are decreasing the distance, so it is moving on this side, and the hydrogen atoms are coming closer together and the energy is decreasing, and it is going to this minimum point. This is the bottom of this well, and at this point it is minimum. And again, if the hydrogen atoms they come further closer together, then the interaction energy it starts increasing, and you can see here it goes upward, and it can even go beyond this zero value and become positive. So what is this point? This point at which this is the distance at which the interaction energy is minimum, or negative, most negative between the two hydrogen atoms. And if you calculate this distance, this will be equal to 0.4 angstrom, which is actually the bond length between two hydrogen atoms. So this is the ideal point at which the bond will be formed between two hydrogen atoms. So you can see here that this energy, if you calculate between two hydrogen atoms when they are separated, is minus 2624 kilojoule per mole, and this is the energy at the bottom of the well is minus 3048. And the difference of these two energy, it will give the bond strength of these two hydrogen atoms. So further, if the two hydrogen atoms are separated, then the energy is, you can see here, if the two hydrogen atoms are separated, the energy is higher or more positive, and if you have even the proton separated from the electron, then the energy is positive. So whenever a bond is formed between the two atoms, then the energy becomes negative because they are coming closer together. So if the distance is decreasing, actually the potential energy is decreasing, and you get the negative energy. Whenever the bond is formed, you have the negative energy. Energy is released when the bond is formed. And if we break the bond, then the energy is absorbed because we have to give the energy in order to break a bond, and therefore whenever we have to break a bond, we have to give energy, and it will be positive. And if a bond formation is taking place, then the energy is released and it is represented by the negative value. So this is the interaction energy curve of hydrogen atom, and the shape of this interaction energy curve is similar for the other atoms as well when the bond is formed. However, this value of energy is different for different atoms, because it actually gives the bond strength between two atoms, which is definitely different for different atoms. So what is the significance of this interaction energy curve? The first thing that I have already told you is that if you take the difference of this value, the energy when the hydrogen atoms are at the separated atom limit, and the energy at the bottom of this well, then the difference of this energy will give you the bond dissociation energy for the hydrogen molecule. So this also represents the bond strength. The bond dissociation energy is represented by ED here, and you can calculate if you are given this interaction energy curve and these values, and you are asked to find out the bond dissociation energy, you can take the difference of these two values and provide the value of bond dissociation energy. So delta ET for hydrogen is calculated at 3048 minus 2624 to give 424. So here you need to note down that you are not writing the negative sign here, because you need actually to take only the difference of these two values. The negative sign is only representing that energy is released in this process of bond formation between two hydrogen atoms. So 424 kilojoule per mole is the bond dissociation energy for hydrogen molecule. So basically, when two hydrogen atoms they come closer towards each other, the covalent bond is formed. And what is a covalent bond? A covalent bond is actually formed when the two electrons are shared between two hydrogen atoms. So here you can see this is one of the hydrogen atoms, and when they come closer towards each other, the two electrons they are shared between two hydrogen atoms, and this is the bond energy of and therefore in the two hydrogen atoms singular one hydrogen atom has the energy of 1312 kilojoule per mole, and if you multiply it with 2 you will get 2624 kilojoule per mole. So you can see that from where the this energy of the separated hydrogen atoms is coming from. If you go back to the interaction energy curve, here this is the value 2624. So you can also write down or explain from where this value is coming from. You have the energy of the one hydrogen atom, and if you multiply it with 2 you get this value. So here there you can see it minus 2624 kilojoule per mole. So energy of the hydrogen molecule is minus 3048 kilojoule per mole, as you have seen from the curve. And this is the covalent bond between the two hydrogen atoms that is formed because of the sharing of electrons. Now, if you are given the interaction energy curves of two molecules, you can also find out the bond strength or compare the bond strength of the two molecules. For example, in this diagram here, you can see that this is the dotted line which represents the interaction energy curve for the nitrogen molecule, and the above one, this one is the one for the hydrogen molecule. So if you are to compare the bond strength of the two molecules, you can easily find out, because if you take the difference of this point and this point, this difference of energy is higher, and the difference of energy between for the hydrogen molecule is lower. So it means you have to provide more energy to break the nitrogen bond, and therefore the bond dissociation energy of nitrogen molecule is higher. So you can also easily see that the bond strength is higher for the molecule for which we have a deeper energy well. And also when you have the higher bond dissociation energy, you have usually the more bond strength, because more bond strength, and also you have a shorter bond. And also you already know that nitrogen molecule has a triple bond, and triple bond is always shorter because that is more stronger, and therefore it requires more energy. And hydrogen is a single bond, and therefore it is a longer bond and it requires less energy. So these all you can all things you can relate with the interaction energy curve and predict the strength of a bond. Now we have seen the basics of the chemical bond formation. What are the interaction energies, which are the general interaction energies which are associated with the formation of bond. We are going to now start the models of the chemical bonding. The first and the most basic model is the Lewis structure, which was invented by G. N. Lewis. And he said that chemical bonding is actually due to the overlap of electrons from each atom. So the idea of Lewis structure is that he takes the total number of valence electrons of atoms and then redistribute them so that each bond between two atoms, it gets two electrons, and the rest of electrons they are distributed between the combining atoms so that each atom has a complete shell. Now we are going to do this in certain number of steps to understand it. For example, let's see first the fluorine molecule. Each fluorine atom has 7 valence electrons, and each fluorine atom has 1 electron that is shared between them, and the rest of the electrons are lone pair. So if you see in this diagram, we have 7 electrons for each atom of hydrogen of fluorine, and we have a single bond between fluorine, and you can see 2 electrons are shared in this bond, and the rest of the electrons they are distributed on the atoms in such a way that each atom has a complete octet. So hydrogen is an exception because it needs only 2 electrons to complete the shell, and it doesn't require octet. In HCl, if we see, we have hydrogen has 1 electron, and we have chlorine which has 7 electrons, because chlorine is present in the 7th group. It is a halogen, and when we have a 7th group, it means it has 7 electrons in the outermost shell. So what happens is that the single bond is formed between hydrogen and chlorine, and you can see that 1 electron here and 1 electron from here, they are shared between the two atoms. So if we want to draw the Lewis structure of these molecules, we have to follow a certain number of steps. But we should keep in mind that hydrogen has a special stability with 2 electrons, and most of the other atoms, they have special stability associated with the 8th number of electrons, which is called as octet. So before going to drawing the structures using the Lewis diagrams, we first need to describe that what is the bonding electron and what is the lone pair electrons. So bonding electrons will be those that are shared between the two atoms in the bond. That is, for example, here in the HCl molecule, the 2 electrons will be called as the bonding electrons. And the rest of electrons which are not shared between the bonds, then they are called as the lone pairs, like 1, 2, 3, 4, 5, 6 are the lone pair electrons, or you can say that there are 3 lone pairs. Now the Lewis structures are not correct 100% of the time, but they do predict the configuration of the molecules 90% of the time correctly, and therefore we still use the Lewis diagrams for predicting the structure of molecules. Our other option is to solve the Schrodinger equation, which is a very tedious task for higher molecules. Now let's draw the Lewis diagram using the rules which are put forward by the J.N. Lewis. Again, we have said that the basic idea is that we have to calculate the total number of valence electrons of the two atoms, and then what we will do, we will assign 2 electrons to each bond between the atoms, and the rest of the electrons, they will be distributed between two atoms in such a way that they have the complete shell. Let's start from the very basic example of CH4 molecule, which is called methane. The first step will be that we have to draw the skeletal structure of the molecule. Okay, the skeletal structure is like this. Here you have put carbon in the center, and we have attached hydrogens on the 4 corners of this carbon. We can have these lines, they represent that hydrogens are bonded with the carbon atom. So this is the basic skeletal structure of the methane. We cannot put hydrogen in the center because we know that hydrogen forms only 2 bonds, and the only option is to put the carbon in the center and place hydrogen atoms around this carbon atom. So this is our only option to draw the skeletal structure of the methane. The second step is that we count the total number of valence electrons of all combining atoms. So if you have hydrogen, which has 1 electron, and because you have 4 hydrogen atoms, so it means there are 4 valence electrons for 4 hydrogen atoms. Carbon has 4 electrons in the outermost shell. So what happens is that we have total valence electron 4 plus 4, which is 8. Now we go to the third step. That is, we have to count the total electrons that we need if each atom has a complete shell. So we want to calculate the total electrons that are needed to complete the shell in each atom. So 2 electrons are required by hydrogen atoms to complete shell, and we have 4 hydrogen atoms. And 8 electrons are required by 1 carbon atom. So what is this total? 8 plus 8 is equal to 16. So we have total 16 electrons that are required if we want to have a complete shell for hydrogen atoms and for the carbon atom. The fourth step is that we calculate the number of bonding electrons, and this is calculated simply by subtracting this number, which we have calculated in the second step, from this number 16. That is, the total number of valence electron will be subtracted from the total number of electrons required to complete the shell. So you get 16 minus 8 is equal to 8. So these are the bonding electrons. It means we have to assign these 8 bonds 8 electrons to the bonds that we have drawn in this molecule. So the next step is that we assign 2 bonding electrons to each bond represented by a line in the diagram. So this was the basic rule of Lewis diagram, that we have to assign 2 electrons to each bond. So we have 4 bonds here, and what we do, we assign 2 electrons represented by these 2 white circles to each line or each bond. So in this way we have assigned 1, 2, 3, 4, 5, 6 and 7, 8. Total 8 bonds, total 8 electrons are assigned to these bonds. Now sixth step is that we have to check if extra bonding electrons are remaining. So in this case no, because we have utilized all the 8 electrons. Now seventh step is that you can see any valence electron left. That is, you have to check that the bonding electrons are equal to the valence electron. If they are equal, it means all of the valence electrons are utilized in bonding. So we have to check that the valence electrons are the same as the bonding electrons. So here we can see that no valence electron is left. All of the valence electrons, they are utilized. And this is the Lewis structure of CH4, where you can see carbon has octet 1, 2, 3, 4, 5, 6, 7, 8. And also hydrogen has the complete shell because it has 2 electrons, 1 and 2. Now let's draw the HCN molecule. First step is again to draw the skeletal structure. Now here you have three atoms, so nitrogen, carbon and hydrogen. So you have to decide that which atom has to be put in the center. So in such a case, you have the rule that you have to put that atom in the center, which has the low ionization energy. You cannot put hydrogen atom in the center because hydrogen has to make only one bond. You can either put nitrogen or carbon, and here you can see that carbon has the low ionization energy as compared to nitrogen. Carbon is present in the 4th group and nitrogen in the 5th group, and as you move from 4th to 5th group, the ionization energy increases, and therefore we have carbon which has low ionization energy. So we have put this carbon in the center and nitrogen on the sides, and these lines, they represent the bond. The second step is that we calculate the number of electrons, valence electrons in the molecule. So you can see hydrogen has 1 valence electron, carbon has 4, nitrogen has 5. So 1 plus 4 plus 5 is equal to 10. Now calculate the number of electrons required to complete shell in each atom. So that is 2 for hydrogen, 8 for carbon and 8 for nitrogen. That is equal to 18. Now we calculate the number of bonding electrons, that I have already told you that it is the difference of this 18 minus 10. So you get 8. It means 8 electrons has to be assigned to bonds. The next step is that assign 2 electrons to each bond. Now here you have 2 lines. So assign 2 electrons here and 2 electrons here. So you have assigned 4 electrons, but you can see that we have 8 bonding electrons. So what you do in this case, when you have number of bonding electrons left, if you have bonding electrons left, we make the double or triple bond to utilize all of them. So generally a double bond is formed between carbon, oxygen, nitrogen and sulfur, and a triple bond is formed between carbon, nitrogen and oxygen. So here you can see a triple bond cannot be formed between hydrogen and carbon. It can be formed between nitrogen. So we make 2 new bonds or 2 new lines between carbon and nitrogen to utilize all of the bonding electrons. So in this case, you will see that all the electrons will be utilized: 1, 2, 3, 4, 5, 6 and 7, 8. So 6 here and 2 here. So we have 8 electrons, number of bonding electrons that are utilized. Now you want to see if any valence electron is remaining, that is, if there is a difference of valence electron and the bonding electron. You see here there is valence electrons are 10 and the bonding electrons are 8. So it means now all the valence electrons are not utilized here. So what will happen is 2 is the additional electrons, so they are assigned as the lone pairs to the atom which has not completed its shell. So let's see here, you have 1, 2, 3, 4, 5, 6, 7, 8. Carbon has 8 electrons, hydrogen has 2, Nitrogen has 1, 2, 3, 4, 5, 6 electrons, and we have assigned these 2 extra electrons to complete its shell so that it has a complete octet. So if the valence electrons are remaining, you will assign them as the lone pairs to the atom which has not completed its shell. Now there is another example of thionyl chloride, SOCl2. The first step is again draw the skeletal structure. Halogens are usually terminals. We have SOCl2, so chlorines, they also make one bond, therefore they cannot be placed in the center while drawing a skeletal structure. So they are also terminals like hydrogen. Now we have oxygen and sulfur. So we have to pick the atoms with the low ionization energy. Sulfur has a low ionization energy, and therefore sulfur is put in the center. And we have placed oxygen here. So this is basically the skeletal structure of SOCl2. Now the second step is calculate number of valence electrons. So you can see oxygen has 6, sulfur has 6, chlorine has 7, and this chlorine has 7 because they are in the 7th group, and these 2 atoms are in the 6th group. So we have 7 plus 7 plus 6 plus 6 equal to 26, which is the total number of valence electrons in these atoms. Now calculate the number of electrons required to complete the shell in each atom. So each of these 4 atoms, they require 8 electrons to complete their shell. So we have 8 plus 8 plus 8 plus 8 is equal to 32. Next step is we calculate the number of bonding electrons. Again, it's a difference of 32 minus 26, we get 6. So it means 6 electrons has to be assigned to each line or each bond. So next step is assign 2 electrons to each bond. 6 electrons used up. 1, 2, 3, 4, 5, 6. Here you can see these white circles. These are electrons. 6 electrons have used up. So we will not have any double bond because no valence electron is left here. Now let's see the difference with the valence electrons. Valence electrons are 26 and we have only utilized 6 electrons so far. So we have to utilize all of the 26 electrons, valence electrons. So what will you do? The remaining 20 electrons, they are to be assigned to the atoms to complete their shells. So assign these electrons, like you can see here, the red ones, the red dots, these are the 20 total. And we have assigned them to the atoms so they have complete shell. So by following the Lewis rules, you can make the thionyl chloride structure, which appears to be like this. So this is the summary of the rules, Lewis structure, rules for drawing the Lewis structures. There is one additional point that I have added here, that sometimes you have the negative ions or positive ions. So if you have a negative ion, then you will have to add the absolute value of total charge to the valence electron, and if you have a positive ion, then subtract minus that value from the total number of valence electrons. The other steps are the same as we have done. Now let's see one example with the negative ion. There is a cyanide ion Cn-1. The first step is that we draw the skeletal structure Cn. Number of valence electron we count is 4 for the carbon atom and 5 for the nitrogen atom. We are adding plus 1 because we have a negative charge on the ion, so which represents that it has one additional electron. So the total valence electron will be 4 plus 5 plus 1 is equal to 10. Now number of electrons required to have a complete shell for each atom. So carbon requires 8, nitrogen requires 8, we have 16. Now we calculate number of bonding electrons, subtraction of these two values. So 16 minus 10 is equal to 6. 6 electrons are the bonding electrons. Assign 2 bonding electrons per bond. So you assign 2 electrons to the first bond that you have created, and you can see is here. The white dots, they represent 2 electrons. But you can see that you have 6 bonding electrons. So when you have left bonding electrons, then what you do, you create the double and the triple bond. So we created 2 more bonds to utilize all of the 6 bonding electrons. So 1, 2, 3, 4, 5, 6. We have utilized the bonding electron. Now check that if we have any valence electrons left. Yes, because we have 10 valence electrons. So it it means 4 electrons are remaining which needs to be utilized, and we can utilize it by assigning it to the atoms which have not completed their update. So what you do, you assign 2 electrons to carbon and 2 to nitrogen, and therefore you have complete shell for both, like 1, 2, 3, 4, 5, 6, 7, 8, and here for carbon 1, 2, 3, 4, 5, 6, and 7, 8. So in this way you will draw the Lewis structure of the cyanide ion. Now formal charge is a concept which is associated with Lewis structures, and it is used to actually confirm the correctness of the Lewis diagram. So formal charge is actually calculated by this formula: valence electron minus lone pair electrons minus 1 by 2 of the shared electrons. And if you have a neutral molecule, then the formal charge on each atom has to be calculated, and the sum of the formal charge on each atom should be equal to 0 if you have a neutral molecule. If a molecule has a -1 charge, then the sum of the formal charges on all of its atoms should be equal to -1. Now let's check it for the cyanide molecule again. We have CN which has -1 charge. First calculate the formal charge on carbon. That is equal to valence electron minus lone pair electrons minus 1 by 2 of shared electrons. Carbon has 4 valence electrons. It has 2 valence electrons in the Lewis structure, minus 1 by 2 of 6 because there are 6 electrons shared between them. So we get -1 charge on carbon in the Cn -1. Now formal charge on nitrogen, similarly valence electrons minus lone pair electrons minus 1 by 2 of the shared electrons. Valence electron in nitrogen are 5, minus lone pair electrons are 2, minus 1 by 2 of 6 because 6 electrons are shared, you get 0. So here in this Cn -1 ion, basically the negative charge is on the carbon atom and it's not on the nitrogen atom. Most of the people think that it's on the nitrogen atom, but it's not on the nitrogen, it's on the carbon atom. So if you add these two formal charges, you will get -1, which is actually the charge on the molecule. So this shows the correctness of the Lewis diagram. Similarly, for thionyl chloride, you can calculate the formal charge on sulfur +1, formal charge on oxygen -1, and formal charge on each chlorine atom, which is 0. So overall -1 and +1 plus 0 plus 0, you get overall 0 charge on the thionyl chloride. So it shows that the Lewis diagram is correct for thionyl chloride. So what is the application of formal charge in Lewis structure? We use formal charge to make sure that we have drawn the correct Lewis structure, and the structure with the lowest formal charges on atoms is the most stable structures. Sometimes if you have more than 2 Lewis structures drawn and you are confused that which of these structure is the correct, so what you will do, you will calculate the formal charges on the two structures, and you will have to see that which of these two structures has the lowest values of the set of charges. That structure will be the correct one. Let's do an example. For example, we have NCS, and for example we have 3 structures for the thiocyanate ion, and we have carbon, sulfur, and nitrogen. And if we draw based on the ionization energy, we will predict that central atom to be the atom with the lowest ionization energy. So the lowest ionization energy is for the, here you can see that it's for the sulfur, and based on this sulfur should be in the center. But let's hypothetically draw 3 structures where we have carbon in the structure A in the center, in the structure B we have sulfur in the structure, and in structure C we have nitrogen in the center. And if you draw their Lewis structures by following all the rules, and then you calculate the formal charges on each atom in the structure A, and you calculate the formal charges on each atom in the structure B, and calculate formal charges on each atom on the structure C. So here you see you have -1 charge, 0 and 0. In structure B you have -1, -2 and +2, and here you have +1, -2 and 0. So here you have to see that the structure which has the lowest set of charges. This one, the structure A, has the lowest set of charges. So we can say that this one is the structure which is more stable. So in this case, this structure is more stable, and in this way the formal charges predict the correctness of the Lewis diagram. Here are some practice questions for you. You can draw the Lewis structures of the molecules and explain the fundamental interaction using interaction energy curve when a bond is formed between two hydrogen atoms. So this is all for today's lecture. In the next lecture, we are going to study the other model of the chemical bonding, which is the molecular orbital theory. Thank you.